Commander, tear this ship apart until you found those plants. Sorry, everyone. A little carried away there. This is Josh Price, and welcome to Chemistry 352 Online. Today, we're going to pick up where we left off when we were in class. We'll spend a couple minutes talking a little bit more about the Robinson annulation, then we're going to move on to Chapter 29. I hope you're all healthy and happy, having a good time, and keeping your social distance from people around you. All right, so when we were together last, I had drawn for you a Robinson annulation product, and I had asked you to think about what the starting materials would have been. And I believe we got mostly through that problem, but then I think all hell broke loose with the coronavirus, and so my guess is that some of you hadn't thought about it for quite a few days. So we're going to take just a step back and try to review what we know about the Robinson annulation. All right. So the first key observation is that anytime you see a cyclohexenone, that could have been made via the so-called Robinson annulation, which is just a Michael reaction followed by an intramolecular aldol reaction. At this stage, it can be helpful to label the carbons in this cyclohexenone ring in a way that will help us see where these, what the starting materials for this product would have been. So I'm going to use the color blue for this carbonyl carbon. On the bottom hand side, I'm going to use pink for alpha carbon and pink for beta carbon. I'm reminding myself that the sigma and pi bonds between alpha and beta carbons here would have been made by an intramolecular aldol reaction in which the alpha carbon was the enolate and the beta carbon now would have been the carbonyl carbon of the electrophile in the intramolecular aldol reaction. Similarly, on the other side, I'm going to label this carbon alpha, this carbon beta, and the carbon beyond beta, I guess, we can call gamma. And sure, we'll put it there, gamma. And we'll remind ourselves that there used to be a pi bond between the alpha or yellow alpha and beta carbons, and that the gamma carbon used to be the alpha carbon of an enolate. Okay, so the bonds we made in the Michael reaction is this bond in our product between beta and gamma carbons, and then the bonds we made via the intramolecular aldol reaction are the sigma and pi bonds between pink, alpha, and beta carbons. Okay. So with all of that in mind, we can go all the way back to what the starting materials would have been. We can draw the carbonyl compound. We'll call this one C and this one, alpha. We'll remind ourselves that carbon C gets attacked by the enolate, and we'll also remind ourselves that in the Michael reaction, alpha carbon attacks beta carbon of alpha beta unsaturated carbonyl compound and thereby becomes the gamma carbon, whereas the pink carbonyl carbon becomes a beta carbon. And then over here, the other part of the molecule, we have our carbonyl carbon, our, let's see, alpha carbon, pi bond between yellow alpha and yellow beta. And of course, yellow beta gets attacked in the Michael reaction, whereas the alpha proton here attacks the pink carbonyl carbon. All right, so when you draw the Robinson annulation product as we did here, with the ketone in the lower right-hand quadrant and the pi bond between pink alpha and beta carbons in the bottom edge of our six-membered ring, then then you can sort of have a then you can sort of draw a line down the molecule like that and separate it into two separate parts. Now, if you weren't able to see this answer or figure out where it came from, I'm going to invite you to pause and try to think about this reaction in the forward direction. That is, draw a mechanism of the Michael reaction followed by the intramolecular aldol reaction. So pause the video and do that. And now that you've done that, let's review it together. All right, I'm going to, for the sake of speed and realizing that you can pause the video at any time to try to get caught up, I will show you the Michael reaction. First, we're going to have hydroxide act as a base to remove the alpha proton. That's going to give us an enolate, which I'm going to draw here. Negative charge on yellow alpha carbon. It's at that stage that we can show the negative charge of our enolate attacking the beta carbon of our alpha beta unsaturated carbonyl carbon. Remember that what that basically means is the enolate is dumping electron density into the LUMO of your alpha beta unsaturated carbonyl compound. The LUMO is an antibonding orbital, and the pi bond between alpha and beta has to break. We can push electrons from that bond between alpha and beta to be on just the alpha carbon. Doing this allows us to draw the following intermediate, and I'm going to try to use color to illustrate the new bond that we just made. this is still carbonyl carbon. This is still pink alpha. This is still yellow alpha and beta. Now that we've made that bond, we'll call this one, oh shoot, got a color problem there, sorry folks. Egregious waste of class time on coloring. We'll have lone pair electrons on that yellow alpha carbon. We will, oops, like red there, we will protonate that enolate. And then, if it's all right, I'm going to just recopy this portion of our molecule and draw it here. Again, if you need to pause to get caught up, that's fine. At this stage, we will have OH minus remove the proton on pink alpha carbon, generating a new enolate. And the key feature of, this enolate is, did it again. Key feature of this enolate is that it would have a negative charge on an alpha carbon that is 6 atoms away from pink carbonyl carbon. And so the intramolecular aldol reaction can work quite well here. Attack, I don't like that arrow, sorry folks. We're going to attack the carbonyl carbon to get a tetrahedral intermediate. So let's just draw what that tetrahedral intermediate would look like. Here is the bond in pink. And we will take lone pair electrons on that oxygen. We'll protonate that negatively charged oxygen in the tetrahedral intermediate with using water. And the product of that reaction is this, beta hydroxy ketone, which is an aldol product. I will point out that now that we've made the bond between pink carbonyl carbon and pink alpha carbon, we're going to rename the carbonyl carbon as beta. So this is a beta hydroxy ketone. That's an aldol product. But to get to the Robinson annulation product that we've drawn before, we need to do the elimination reaction, which is going to involve hydroxide as a base, removing a proton from pink alpha carbon. Sorry about that. Here's the lone pair electrons on the alpha carbon. And then in the final step, electrons will kick down from that enolate and kick off the OH minus group to give you your desired Robinson annulation product shown here. Okay. All right, so I want you to be able to look at a cyclohexenone product and tell me what the starting materials would be. I want you to be able to draw the mechanism of this two reaction series. And that is basically all we need to do with chapter 24. At this point, we're going to move on to chapter 29. You've got a study guide for that, and the study guide tells you that you're going to focus on three key Nobel-Prize-winning reactions. These are reactions that are highly synthetically useful. They're fairly modern, that is, they were discovered within the past 40 years or so, and they've really revolutionized how people prepare molecules, especially in the pharmaceutical industry. So we're going to talk about the Heck reaction, the Suzuki reaction, and then olefin metathesis. And I'll want you to know how to use these reactions in a predict products or provide reagent sense. I'll want you to know how to use them in a synthesis. I do not want you to worry about the mechanism for these reactions. It's included in the Smith text, and you can peruse it as you like. Sometimes if you haven't spent some time with the mechanism, it's hard to remember how the reaction works, but I'm not going to ask you any questions about the mechanism of this reaction. So with that, let's get started. With the Heck reaction. The Heck reaction is an example of a cross-coupling reaction. That is a reaction that will allow you to take one molecule with a particular functional group, another molecule with another functional group, and attach them together. It's sort of Lego type chemistry. And I wanted to give you just a bit of background. This is Professor Heck, who won the Nobel Prize in Chemistry in 2010 for discovering the reaction that is now named after him, and it uses palladium to catalyze reactions that couple aryl halides with alkenes. As an example, naproxen or Aleve is an example of a molecule that can be prepared efficiently using the Heck reaction. So let's give you a sense of the kinds of molecules that work in this cross-coupling reaction. Partner number one is an aryl or a vinyl halide. What do we mean by aryl halide? Aryl halide is a halide that's attached to one of the sp2 hybridized carbons of an aromatic ring. For this reaction, the Heck reaction works when X equals iodide or bromide. This is an example of what we call substrate scope. In organic chemistry, when people discover a new reaction, they pay close attention to what molecules work in the reaction. So this is an example of an aryl halide. This is an example of a vinyl halide. A vinyl halide is one in which the bromo or iodo group is attached to one of the sp2 hybridized carbons of an olefin. So either of those options will work for partner one. And since we like coloring so much, I'll just highlight all of that. And then partner two is going to be an olefin. And the olefin ethylene works okay. But also olefins of the type where they are monosubstituted with some Z group, where Z tends to be something that's sp2 hybridized as well. Sometimes things that are electron withdrawing groups, such as squiggly line indicates the bond that connects the Z group to the vinyl carbon. So this could be an ester, this could be a nitrile, it could even be a benzene ring. All right, so that's the other portion of, oops, don't like that. That's the other portion, the other partner in our reaction process. And the neat feature here, which I'm going to try to highlight, is that the Heck reaction is going to take, oops, I suppose that'll work. It's going to take the hydrogen here and the halide here, and it's going to remove both of those groups and attach the corresponding carbons together. And that's what we mean by a cross-coupling reaction. Now let's talk about the reagents for this reaction. First, you need the palladium-2 catalyst. That's palladium in its +2 oxidation state. A typical source of palladium-2 is in the commercially available compound palladium acetate. Acetate is simply the corresponding, the conjugate base of acetic acid. So palladium 2+ and 2 negatively charged acetates is a neutral compound. Also, in a lot of these reactions, you have things that are called ligands that bind to the palladium and alter its electronic properties. A common functional group for ligands is a class of molecules called phosphines. Note that phosphorus is one row on the periodic table down from nitrogen, and nitrogen-containing compounds, alkyl nitrogen-containing compounds are called amines. Phosphorus-containing alkyl compounds are called phosphines. Here is an example of a ligand that is used commonly in the Heck reaction. The molecule is called triphenylphosphine, and it binds to or chelates the metal and enhances or changes its electronic properties. We'll abbreviate for this molecule for the most part P for phosphorus and then PH3 for triphenyl. And then finally, you need a base. And I'll show you why you need the base in a little bit, but the base we're going to use is triethylamine. This is a sterically hindered non-nucleophilic base, and it is present to soak up the equivalent of HBr that we make in this process. All right, so it's kind of complicated, but let's highlight the reagents that are needed. You've got palladium acetate, you've got triphenylphosphine, and you've got triethylamine. All right, so let me give you an example of a Heck reaction. I'm going to draw our aryl halide, and let's say it's the bromide, and just for fun, let's put the methoxy groups there. And then we're going to couple that with a molecule. It's called cyanoacrylate. It's an olefin with a nitrile group on it. And then maybe I'll adjust molecule this way. The reagents for this reaction would be palladium acetate, triphenylphosphine as ligands, and triethylamine as a base. And remember that this reaction, is going to create a new bond between the carbon I just highlighted in pink and the carbon I just highlighted in orange. All right. And the real utility of this reaction is how specific it is. I'm going to use in red the new bond that we made. Here's the olefin. And it turns out that this reaction is stereoselective for trans stereochemistry about the olefin. That is, the aryl group gets installed on the gets installed in place of the proton that was trans. Or actually, it's just stereoselective for the trans product. The aryl group ends up trans to whatever the group was on the monosubstituted olefin. All right, and that reaction is high yielding. One other example might be useful. Here is an aryl iodide, and here is corresponding olefin reactive partner. Remember, we're going to couple this carbon in orange with this carbon in pink. The reagents we're going to use are these. You will need to know these reagents, and that will probably involve some memorization. Now, there's a couple of interesting features to this reaction that are worth talking about. I want you to note first that the bond that we install on the pink highlighted carbon, the one that used to have the iodide, gets installed in the same direction as the iodide was. That is, these groups are trans here, and these groups are still trans here. So that's a specific feature. And then second, the new bond that we get is always trans to the functional group on our orange olefin. Okay, and notice the kinds of bonds we're making in this process. In both cases, the new bond we made was a sigma bond between sp2 hybridized carbons. All right. So let's take a look again at the Heck reaction and see whether we can find an example. Let's look up naproxen. Well, I guess I didn't find what I was going to be looking for. So that is the Heck reaction. Now I'm going to introduce the Suzuki reaction. Professor Suzuki won the Nobel Prize in the same year as Professor Heck, shared the Nobel Prize. there is Professor Suzuki, and his reaction is one that couples an aryl halide with an aryl boronic acid. So Suzuki is also a cross-coupling reaction. Again, if we were to talk about substrate scope, we could include partner 1 as the aryl or the vinyl halide that we saw as the starting material for the Heck reaction. But partner 2 is an aryl boronic acid, or in other words, some kind of benzene ring attached to boron, and then the boron itself is attached to OH groups. And I won't, your text will probably tell you how you might synthesize boronic acids. That won't be important for our discussion this semester, though I'll point out that they're not that hard to synthesize and some of them are commercially available. The reagents for this reaction involve palladium 0, though over the course of the reaction it looks like the palladium oxidation state cycles between 0 and +2. We won't worry too much about the mechanism for the reaction. The reagents are a source, a catalyst, which I just said was palladium in its 0 oxidation state, neutral. It comes with, you can buy this already bound by 4 triphenylphosphine ligands. So we would call this palladium tetrakis triphenylphosphine. That can be kind of fun to say. And then you also need a base to make the reaction go. The reason for that is not particularly important for us. There are other ligands used. The triphenylphosphine palladium is one that is frequently is a good way to get palladium 0, but sometimes they add other phosphine ligands to modulate the reactivity. Other triaryl phosphines are sometimes used. Your text shows this one. I won't require you to remember this one. This is the orthomethyl type of ligand. And so let's give you an example of a cross-coupling reaction based on palladium. Here is going to be your aryl halide. Let's just let it be the bromide. And then let's have the other partner be the boronic acid. And again, we wouldn't, the pink compound on top, you would be able to synthesize based on things you learned in 352. The boronic acid on the bottom, we wouldn't worry about how to synthesize that. We're going to be coupling carbon in orange with the carbon in pink. So here is the first partner. Here is the new bond we made. And here is the second partner. And it looks like the OMe group would be here. This is a linkage between two benzene rings. It's a biphenyl linkage, and actually there's some steric clashes between the orthoprotons on the orange substituent and the orthomethyl and orthoproton on the pink substituent that requires these two rings to not be conjugated with each other, but rather to be sort of out of plane with each other. And of course the reagents for this would be triphenyl phosphine, tetrakis triphenyl phosphine palladium. And you would presumably also include some kind of triaryl phosphine ligand, and then potassium carbonate as a base. And you make the new carbon-carbon bond, which is again another way of making sp2, carbon-carbon sigma bonds. So that's the Suzuki reaction. Be able to use it in a predict product sense or provide reagent sense. Some of you are likely wondering, well, what the heck? Haha, get it? What the heck? The heck reaction? Some of you are wondering what on earth the palladium does. And there are details on that in the book. Palladium has some interesting properties in terms of what it can do with aryl halides, and we're not going to talk at all about that this semester, but if you're interested in learning more, you can look forward to Inorganic Chemistry 514 in a year or so, and you can also think about taking Professor Michaelis's organometallics class when it becomes available. All right. The last reaction we're going to talk about today is one that we've used before in my research. I think we probably won't have time to talk about the research aspect of my work today, but maybe at the beginning of the next lecture we will. And this reaction is called Olefin Metathesis. And Olefin Metathesis won the Nobel Prize. Let's just look it up here. In 2005, Professors Chavon, Grubbs, and Schrock each were awarded the Nobel Prize for their work on this reaction. And it's a beautiful reaction because it can take two alkenes, clip them down the middle, and reattach them together in a new way. Oops, sorry, struggling with the technology. So in the most popular version of Olefin Metathesis, partner 1 is some kind of terminal olefin. By that we mean something like that. And partner 2 is also a terminal olefin, something like this. And the catalyst, there's different versions. There's a molybdenum catalyst There's ruthenium catalyst that's sort of been pioneered by Professor Grubbs. And there are multiple versions of each catalyst with different ligands. I'll draw for you one of the catalysts. So P is phosphorus, and I'm going to use CY3, where I'm going to tell you that CY equals just a 6-membered ring cyclohexyl group. So that's a phosphorus attached to 3 cyclohexane groups. Then, and those are axial ligands, point up and down with respect to ruthenium, and then ruthenium in the plane. Equatorial ligands include 2 chlorines and then a doubly bonded carbon. They sometimes call that an alkylidine, and you buy the metathesis catalyst already doubly bonded to a carbon. And the beautiful thing about, and we'll call this the Grubbs catalyst, there's a first-generation Grubbs catalyst, and there's a new and improved second-generation Grubbs catalyst that I won't require you to know anything about. But let's imagine that we have these 2 terminal olefins. The Grubbs catalyst is going to clip off the terminal CH2 group for each of those olefins and then attach the remaining carbons together. And this is an equilibrium process, so it would tend to favor the more stable, more substituted alkene product. There would probably be some amount of cis, but the trans would be the major product. And what happens to those CH2 groups that were clipped off? Well, they get stitched together as well. But the thing that helps drive this process forward to the final product is the fact that the 2 terminal CH2 groups get hooked together and become ethylene, which is a gas, and this just bubbles off. And that drives the process towards this final metathesis product. So in the case where R equals orange R equals purple, pink R equals orange R, this is a self-metathesis product. Cross-metathesis products are known as well, but they can be difficult for the same reason that cross-aldol products the cross-aldol reactions can be difficult, because then you can get a mixture of self and cross metathesis products. For example, if R is not the same as orange R, then you would expect to get the following possible products. So that's the self-metathesis product of pink R, the self-metathesis product of orange R, and then the cross-metathesis product and that can be kind of messy. And so cross-metathesis reactions are known, but cross-metathesis reactions work best in making rings. And so what I'll show you now is an example of what's called ring closing metathesis. So I'll draw a molecule that looks like this. If you add the Grubbs catalyst, you can make a new carbon-carbon sigma bond and pi bond between the orange and purple carbons that I've highlighted, and then of course you get ethylene as a byproduct, which bubbles off as a gas. We've actually used the cross metathesis reaction in our research to make a ring or a macrocycle with the goal of using that ring to make a particular protein structure more stable. And perhaps at the beginning of the next lecture, I'll tell you a little bit about that. With that, we'll go ahead and pause. That ends our chapter 29 lecture. Next time, we're going to move on to start talking about amino acids, peptides, and proteins. And we'll continue on from there. And so until we meet again, remember that you don't know the power of the dark side. It's really hard to see to turn off the recording with my helmet on. I can't imagine how Darth Vader sees or does anything.